we have almost finished that your path integral quantum mechanics. Today only one topic which I'll not teach, but I'll tell you how to do it, and then we'll go to the field theory. So path integral quantum mechanics, we know how to calculate amplitude. So you should try for free particle. You can try harmonic oscillator. These are two straightforward to calculate the amplitude in path integral method. Now, one important question is that whether this path integral quantum mechanics and the usual quantum mechanics that we know as, let us say, Schrodinger approach. So, whether they will give you the same result or not. So that is the important question. You have to, it can be proved. Even Arshankar book, you can have the proof. So path integral quantum mechanics and the Schrodinger approach should give you the same result. So that you should follow. And for that, what you have to do, let me tell you. So you just, what you have to prove. I just give you that problem here, and you can do the algebra. So suppose I consider two state in infinite decimally closed. So one at 0 time, at another at epsilon time. So how we can relate them by time evolution in so e to the power minus I h cut epsilon h times psi at 0 time, right? But now we are considering epsilon is very small. So this is normal time evolution, nothing path integral here. So you can write this is 1 minus I by h cut epsilon h times psi of 0. Okay, so infinite decimally closed epsilon. So this you can write, and also you can write in coordinate representation. Say if you write in, this is independent of any basis. So coordinate basis, you can write that psi x at x epsilon should be psi of x0, 0 time, minus I h cut epsilon, and h, if you have a one-dimensional system, minus h cut by 2m d2 dx square plus vx, okay, times psi of x0 time. Okay, so this I can write. Okay, now similar quantity, the same quantity, you can calculate using path integral approach. So this is the quantity you can calculate time evolution through Schrodinger approach, taking that infinite decimal time. Okay, I'm sorry to tell you that BHU facility has withdrawn to record the lecture. So anybody, if you need the recorded lecture, if one student can record it, and then you can send it to me, then I can put the recorded lecture in the YouTube. Otherwise, I'll not able to put, or we can think of going to any other platform like Zoom or something. If you, Zoom, I think number of students is small, and I don't know whether they will permit 1 hour or not. Earlier, they used to permit 40 minutes. But we will think about it. For today, can Nabarun, can you record this lecture, audio plus video? Or anybody else? Hello?
Yes, sir. Then I'll need to download the software, I suppose.
Okay. So anybody, Riyasat?
Sir, my audio will not be recorded.
Okay, Sonam is there or not? Or anybody in the student, can you record? Okay, very good, Vishwajit. Okay, so after recording, you please share with me in my email. Gmail, and then I'll download and put it in YouTube. Okay, so this this is the Schrodinger approach. So this is Schrodinger approach. I know how to calculate this wave function at some infinitesimally close. Now, if you go in the path integral approach, I can write the same quantity x epsilon is that matrix element at x and epsilon and x at 0. So this is 0 time, this is epsilon time, and I like to have different time x prime. So let me write x prime. I'll integrate over it, and then psi of x prime at 0, and then you have dx prime, and this integration is minus infinity to plus infinity. So this is a path integral approach where this quantity is calculated in path integral. So let me write that quantity x epsilon and x prime 0. So this formula you already derived. So this was m by 2 pi I h cut epsilon to the power half, and then e to the power I by plus I by h cut m x minus x prime. This we derive whole square by 2 epsilon. This will give you half mv square kind of term, and then epsilon v, but this was x, and this was x plus x prime by 2, that midpoint prescription. I hope you have not forgotten by this time. Okay, so this is the quantity we know. So what you have to do now, I'll not do anything. This rest of the thing is algebra, maximum Taylor expansion and etc. So you put this quantity here, and starting from this equation, follow the steps in R. Shankar. It is also proved in Ashok Das. So R. Shankar I'll suggest. R. Shankar. Ashok Das, 12 minutes late, Sonam Raj. So R. Shankar book, this has proved. Okay, so follow this proof. If you have any doubt, any question, this is I think chapter 8. Okay, so this concludes the discussion on path integral formulation. Do you have any question at this point? We'll now go to the field theory. Basically, you'll start your syllabus officially, but of course, syllabus in elective course, whatever I'll teach, that will be your syllabus. Any question? If you have any conceptual question, anything, mathematics you will able to follow, but you have to devote time, and final year students are too busy. But anyhow, now we'll move to the scalar quantum field theory. And we'll consider the scalar field theory. Real scalar field theory. That real. This you have learned, but free. Only free version you have learned by canonical quantization. Okay. Now we will consider the interacting. See, not free. Now interacting. So first thing, that free Lagrangian, let us write the free Lagrangian, that was phi and del mu phi, that you know. So it was half m. No, m will come later. Half del mu phi minus m square by 2 phi square. Okay, so this was the free scalar field Lagrangian, and from equation of motion equation of motion you have calculated, that Klein-Gordon equation, which will be box plus m square phi equal to 0. So this is this equation scalar field satisfied. Okay, this step you should know very well, that how to find this equation motion. Okay, now first thing is that how we'll introduce the interaction. How you know that what kind of interaction is will be for the scalar field. So how we know? Interaction. Anybody has any idea how? Suppose I want to study a theory, and that theory, whether it has some interaction or even if it has interaction, which kind of interaction? See, I have only single field, right? Phi is there. I have simplest possible field theory we are considering. So how will find the interaction? Any suggestion? It should be, you should able to give me some suggestion. If you are learning physics, if you are not learning, then this is different story. Okay, so I think you have not. So in interaction, whatever it is, so how I will find the interaction? Whatever interaction, I don't know. Only one field is there, so it is only self interaction is possible. So only self interaction, because only if you have only one student, no teacher, then that student can interact with himself or herself, right? But nobody else is there, so only self interaction is possible. Not only that, that whatever interaction you'll have, that interaction term will obey the symmetries, obey the symmetry. This is the important thing, symmetry of the theory. So what is the symmetry of the theory? Because free scalar field has certain symmetry. So free scalar field, what are the symmetry it has? Riyasat, a free scalar theory.
Rotational and translational.
Translational means phi going to phi plus a?
Yes, sir.
Then mass term will change, right?
Oh, yes, master. Rotational will be there, no?
But rotational, of course, will be there. But what about Lorentz symmetry? Now you people know this. I told you, no?
Yes,
it is Lorentz scalar. It is also scalar. So Lorentz symmetry will be there. Okay. And what else? There is another important symmetry. Now, probably in nuclear physics, you are learning that. And also, you already know gauge symmetry. I also mentioned gauge transformation for Maxwell and also for KG equation, Dirac equation, gauge symmetry must have done. I don't know because I was checking your copies and I found that your relativistic quantum mechanics, I don't know, it was taught by our section, particularly in this, but so many stupid thing you are doing in the copies. But anyhow, gauge symmetry, how you know gauge symmetry? That regarding the Maxwell equation. So Maxwell equation, that we know gauge symmetry. So whatever symmetry free theory has, we expect that it will also be obeyed by interaction. For example, I cannot write a phi del mu phi. This is of course an interaction, or phi square del mu phi. This is of course an interaction term because this term is not present in the Lagrangian. So it is also of course an interaction, but this is not Lorentz invariant. Okay. So this cannot be a interaction term. Okay. But don't go with the derivative. So derivative terms, problem is that if you have higher derivative, for example, if you have phi square del mu phi, this is of course a valid interaction. But it has a 2 more order derivative. Okay. But we are looking for simplest possible interaction. This is of course derivative interaction. Derivative interaction means interacting through momentum. Momentum and derivative, you know, they are related, right? Okay, so possible interaction, okay, phi q, phi 4, this suppose they're phi 5, etc. So 3 field together, they interact. 4 field together, they can interact. 5 field together, they can interact. Or in general, phi to the power n can interact. But we are looking for only simplest possible interaction. So simplest possible interaction looks like to this. Only 3 field interacting together. So let us start. So my Lagrangian will be then half del mu phi m square by 2 phi square, and say I write plus or minus whatever you want, lambda times phi to the power 3. Lambda is the interaction strength or coupling. It is known as coupling. That how they couple each other is given by this lambda, is a number. But now I'm going to tell you that this is not possible. There are some arguments which I'm going to give you. So if this is your potential Lagrangian is kinetic minus potential energy. So if you consider a Hamiltonian or a Hamiltonian density, it will be pi square by 2m, and then you will have half grad phi square, and then you have half m square by 2 phi square plus lambda phi 3. So if you find the Hamiltonian, then Hamiltonian or Hamiltonian density, Hamiltonian will be integration over this. Right? Everybody can have this Hamiltonian, no difficulties. In last semester, I taught you how to find the Hamiltonian. But now, what will happen? See, I expect that any theory, any quantum theory or any theory will be in some point of time will be in equilibrium at some point of time. Whatever it is, it may be at a very long time, after a long time, but it has to be in equilibrium, it will come to an equilibrium. And generally in quantum theory, this when particle reaches or the system reaches at the ground state. Ground state. That will be my ground state is the lowest possible energy. Okay, so when the system reaches ground state, lowest possible energy state, it will not go anywhere further, and it will be then equilibrium. But now, suppose my phi can go to infinity. So suppose my phi going to minus infinity, and suppose we assume lambda greater than 0. Suppose I start with lambda greater than 0. It can be, the argument can be valid for lambda less than 0, that also. So if phi going to minus infinity, lambda is positive. So your in a Hamiltonian energy, the lowest possible energy, ground state energy, will go to minus infinity, because this term will be dominating term. This is phi squared, this is also squared. So this term will be dominating, and phi going to minus infinity, your ground state energy will go to minus infinity. For if suppose lambda less than 0, Lambda less than 0, phi going to plus infinity, again your ground state will go to minus infinity. So if I take a odd power of phi as my interaction, for example, phi 3, phi 5, phi 7, then this problem will happen. No lower bound. This situation is called technically no lower bound of the system. That means no ground state of the system. And in quantum theory, if there is no ground state, then particle will not be stable. That you have learned in Dirac hole theory also, negative energy states. So no lower bound of the system. So system is not stable. And such theory is not acceptable. Is not acceptable. Okay. Okay. So any power. So my simplest possible candidate was phi 3, then phi 4, then phi 5, etc. So this is now ruled out. So simplest possible simplest possible interaction is phi to the power 4. And in phi to the power 4, this problem will not be there. If your it is always going to infinity, phi will go to always will go to infinity, either in minus infinity or plus infinity. This term always will go to the plus infinity. And we choose, if I put my Lagrangian term is lambda phi to the power 4. So let me write again del mu phi minus m square by 2 phi square minus lambda phi to the power 4. So in this situation, I'll write lambda greater than 0. This we are choosing. If we want to have a lambda less than 0, then we'll put this term is negative. So this term sign is in our hand. So now in your Hamiltonian, it will be plus lambda phi to the power 4, okay, apart from all the terms, and lambda greater than 0. So phi going to plus minus infinity, your energy or energy density will go to plus infinity only. Lambda greater than 0 and phi to the power 4 will get than. So excited state energy, I can have anything. So these are excited states. So there is no need for upper bound. No need for upper bound. That you know, harmonic oscillator. Is there any bound? En equal to n plus half h cut omega. You know n can go to infinity. So this can be infinity. So there is no upper bound needed because the excited state energy can be anything. So it is a valid theory. Okay, so now we have found that our Lagrangian. So interacting scalar field Lagrangian is now half del mu phi. I'm writing fourth times or fifth times the same m square by 2 phi to the power 4 minus lambda phi to the power 4. And for some our convenience, we'll write a factorial 4. So this is for our convenience. That later we'll see that lot of term will arise from here which will cancel this factorial 4 term. So this is my Lagrangian, where m is the called mass term and lambda is the coupling term. So any question up to this? How we obtain the interacting theory? You know the Higgs boson. You learn in those who are in particle physics, nuclear physics group. They will learn that standard model of physics and standard model that Higgs particle. They have this interaction, phi to the power 4 interaction. That means 4 scalar particles interact at the same point. So this is the meaning of that.
Sir, you have say no need for upper bound. That please explain.
So when you study a quantum theory, we need a ground state lower bound. Lower bound means we need a ground state. But upper bound, it can be anything. Now, if you give more and more energy to the particle will go a higher and higher state. If you can provide infinitely large energy, particle will go to the infinitely large energy state. So it is a valid theory. No conceptual difficulties. But if there is no ground state, so hydrogen atom ground state is minus 13.6. Suppose I think there is no lower bound. So particle sitting in the ground state 13.6 say, can have release some energy and go to the lower state. Suppose in 50 minus 50, then minus 50 state particle still can release some energy and go to minus 100 state. But there is no lower bound, so that particle will go continuously to up to minus infinity. So this is the called instability. When particle will reach equilibrium, that means the ground state, that is the stable. Then system is stable. But when there is no lower bound, particle will never be stable. So that I am saying. But that is same thing is not problem for higher energies. Higher energy you can have. So if you provide more and more energy, particle will go higher and higher state. So no problem conceptual. So this is the, okay?
Okay, sir.
So, sir, according to you, our stability is like defined by the ground state only.
How otherwise how will define? Tell me.
Like, if what you just said, ki there should be some appropriate ground state. What if
No, I'm
and there
saying
is
that
no need for any upper bound. So the particle, if it will start going to the higher and higher level, so that will not affect its stability.
no, particle cannot itself cannot go higher and higher state. You have to put energy, then it will go. But particle can lose energy. You understand? That is the point. So
Yes, sir.
particle cannot gain energy by himself. Particle can lose energy. Gaining energy, you have to supply the energy from outside. So that you example, harmonic oscillator. Uh, so if you excite the particle, it will go n equal to 1, n equal to 2, n equal to 3, and depending on how much energy you are providing, it will go upper and upper state. But when suppose particle is n equal to 2 state, then particle can lose energy, it can lose energy and can go down. For losing energy, you don't have to do, particle can by itself, it can naturally can lose. Then, but now once it reach a ground state and no further energy level is available in down, it cannot lose further energy. So it has to be stable at the ground state. But if there is lower energy available, particle can further lose energy and go to the lower energy. And but there is no lower bound, particle will continuously go to the lower and lower energy. This we must have studied in case of negative energy state. For Dirac theory, you have this m0 c square and minus m0 c square, and this is forbidden. This region is forbidden. So particle continuously can have any positive energy, and also according to equation, this also can have any arbitrary negative energy. So once particle cross this barrier, that means somehow it has lower energy, particle can jump. And in 10 to the power minus 8 second, all particle will jump to this negative energy state. 10 to the power minus 8 second, if you have an electron system with an arbitrarily negative energy, they will all jump in 10 to the power minus 8 second. Around this number is not too accurate. But I'm what I'm saying, that system will be stable only when There is no lower, there is a definite lowest energy state. So according to then that lowest energy, it will not go any further lower. It cannot go because that will not be permitted by your theory. Okay. Any other question?
So I have one.
Huh.
So the m here we have in the expression minus m square by 2. That m, is it the mass of the particle that we get after quantizing this free scalar field?
Yeah, that will come out. See, here there is no particle. You are discussing the field. Now, when you will go to the Fock space, when you have a quantized theory, suppose you consider your field in a box, then you will have a quantized theory. And then quantized theory that will have a quanta, concept of quanta. So every quanta will have some momenta, some mass. Those have a particle interpretation. So if you have a particle interpretation, then that particle will have a mass m. So, so naively we say that this is a scalar particle with having mass m. But we are doing field theory. Yeah. Any other?
So after applying that creation operator on vacuum space, the particle that we get will have the same mass as written in this expression m.
Yeah. This mass will have the same, but you can have number of particles you can change. That you know in field theory, right? If you have energy, then energy can convert into mass and we can have more particles. So if you started with few particles, it can have the number you can change, and field theory can deal with the when the number are changing. That we have detailed discussion in free scalar theory. Okay. Is that clear, Sitesh?
Yes, sir.
Okay. Okay. So okay. So this is fine. So our theory is now fixed. This is the lowest possible theory, and interaction in quantum field theory is extremely difficult. This is the simplest possible theory, and in few classes you will learn that how much lengthy things you have to face to tackle this term. Simplest possible interaction. Similarly, just in the will come later, when you consider electrodynamics, quantum electrodynamics, electrons dynamics, right? So there you need a Maxwell term. So for electromagnetic, Lagrangian is mu nu. Okay, and electrons are fermion, so you need a fermion terms also. Dirac, Hamilton, Lagrangian. This is your Dirac, but this is electromagnetic. This is Dirac. No interaction between them. Now, how the interaction? This is you know the photon, light particles, and here you have the electrons. So how electron and photon they will interact, and that gauge invariance of this is not gauge invariant. You know this term is not gauge invariant. So gauge invariance, if you demand gauge invariance, then this Lagrangian, by demanding gauge invariance, will modify to this term to a capital derivative term, d mu, where d mu is equal to del mu minus I e lambda. No, just a moment. Del mu lambda. Oh, no. This I wrote wrong. Let me write. Del mu minus I e mu. Photon field will come here, and then photon and psi they will interact. So two fermion and one photon will interact, and that will come from gauge invariance. So this I'll discuss later when I'll come to this field theory, quantum electrodynamics, and that is the main thing you learn here, quantum electrodynamics. But just wait. So I just want to comment that gauge invariance again will give you the interaction. Gauge invariance is the most important. The two most important symmetry is the Lorentz invariant and gauge invariant. Lorentz invariant is of course there. Here gamma mu, mu, nu. Okay. Okay, so now two important thing which we'll later need, I should introduce, then we'll go to the other things, interaction things. So first thing, you should find equation of motion. That I'm not doing for you, but you can able to find equation of motion. This is very easy. You have to differentiate only this term additional. Otherwise, so you find the equation of motion. Okay, now I want to introduce the concept of natural unit because that will be very helpful. Natural, of course, it is not very natural to us. Natural unit, but in particle physics, field theory people, they thought this is a very natural unit. Unit is that when you take h cart equal to 1, c equal to. So you put the velocity of light as 1 and Planck's constant on 1, and this they consider as natural unit. So what is the consequence of that natural unit? That I am going to tell you. So you are taking the c equal to 1, that velocity dimension is lt minus 1, and you are taking this is a number, so dimensionless. This implies that dimension of length is same as dimension of time. Then only it will be a dimensionless. Okay. Now h cart. Next you are taking h cart Planck's constant equal to 1. That means you are making the dimension of this also 1. So Planck's constant is energy arc second, right? So energy is force ml t to the power minus 2 into L. So energy into T. So this is the dimension of Planck's constant, also angular momentum, I think. So you can find it is m L square T minus 1. This is T. But now I have already L equal to T. So L equal to T, so this will be reduced to, let us write T eliminate. So it will reduce to ML. And this dimension also has to be, this is number, h cut is 1, so this is also be dimensionless. Okay. That means mass dimension is equal to length dimension. No, 1 over length dimension inverse. So everything in field theory, now in quantum field theory or in most of the particle physics, field theory, will only one dimension will be used, either mass dimension. Mostly we use mass dimension, or some people use length dimension. So length and mass dimension, they are inverse to each other. So instead of 3 fundamental dimension, mass, length and time, by choosing this unit, I can reduce it to only one fundamental dimension. And let us, for the time being, let us consider mass dimension. So everything will be mass dimension. So now first exercise that we should do, what will be the mass dimension of phi? What will be the dimension of m in our Lagrangian? What is the dimension of lambda? These three things we have to find. How will do that? This is very easy. So let us first concentrate our Lagrangian or action. Action is d4 x, then L, half del mu phi minus m square by 2 phi square minus lambda factorial 4 phi to the power 4, right? But this action, what will be the dimension of action in natural unit? Action is angular momentum, or an angular momentum dimension we made 1. So action is dimensionless. So S is dimensionless. Other way to know it, that you have e to the power I h cut S, and any quantity in the exponential will have dimensionless. So S will have dimension of h such that they will cancel. So the S is dimensionless. So left hand side is dimensionless. So let us write m to the power 0, right? mass dimension. And right hand side, we will calculate the equate and find the dimension of phi. So let mass dimension of phi is mass dimension of power, say, alpha. Well, we find what is alpha. So now matching, left hand side is m to the power 0, right hand side d4x. What is the mass dimension of d4x?
M to the power minus 4.
Uh,
M to the power minus 4.
m to the power minus 4. Good. And then I have phi, 2 phi, so m to the power 2 alpha. And there are derivative. So derivative, but derivative means denominator. So m to the power 2. Okay, I think it is clear. Derivative means 1 over length, right? So that mass dimension to the power 2 derivative in this term. 2 phi, so 2 phi to the power alpha. So you find that 2 alpha minus 2 will be 0. How? This is 2 alpha, this is minus 4, minus 2. So this is m to the power 2 alpha minus 2. And right hand side is 0, so 2 alpha. So alpha dimension, alpha equal to 1. So now we found that dimension of phi is m to the power m, or L to the power minus 1. This immediately. So phi dimension. Now considering the second term. Second term, I now dimension of phi is known. I will find the dimension of. So let us assume that small m dimension is beta. So second term, again right hand side is, left hand side is m equal to 0. Right hand side m, first term is d4, so minus 4. Second term is m dimension I have assumed beta, so plus 2 beta. Then phi square dimension is 1, so plus 2. 2 phi is there. Okay. So again, if you compare, you will get beta is also 1. That means dimension of m, the small m, is the dimension of mass. And this parameter, that is why interpreted as the mass of the theory. So m has the dimension of mass. Now what happened to the dimension of lambda? So fourth term we can calculate dimension of lambda. So again, left hand side is m to the power 0 because action. Right hand side you have lambda dimension. Let us it is delta. So m to the power delta, only one lambda, so delta. Then there are 4 fields, and field dimension is m to the power 4. Oh. Field is m to the power 4. What? Oh, there is also 4, no? I missed that point. There is this d4x dimension I have not considered. So first d4 dimension is minus 4. Then there is a delta from lambda, and therefore from the fields. So what will be the value of delta?
0.
0. So this is dimensionless. So lambda is dimensionless. And this has a very important role in 4th dimension natural unit. If your dimension is not 4, if it is 2 dimension, then it will be 2 and everything will change. So whatever I do the calculation, everything will change if my dimension is not 4. So space-time dimension, we generally consider 4. So in 4th dimension natural unit, this lambda, mass, etc., this dimension are given like this. Okay, so now it is your homework to find dimension of the Dirac field, dimension of the gauge field. These 2 dimensions, find the mass dimension. So you have to consider the Lagrangian for Dirac field, you have to consider for the Lagrangian for electromagnetic field. and find the mass dimension. So this you can do very easily, but try to do yourself. And in 4 dimension, 4 space-time dimension. Okay. So if you have 4 space-time dimension, then try to find this dimension of these quantities, and also dimension of the E or alpha. Try to find the dimension of E. E is appearing in the interaction with uh, electromagnetic and you remember that when I wrote gas transformation. Yeah. So E is appearing here. So from there you can find the dimension. Okay. So this is now next thing what we'll do. So now everything we have done. So let me write my path integral. So path integral. So now in this has a vacuum to vacuum transition amplitude. So this is a vacuum at t equal to minus infinity. This is a vacuum at t equal to plus infinity. And this expectation value, as we know in path integral, can be written d phi e to the power I h cut s. Right? This we know from quantum mechanical path integral. This is long ago we system was equilibrium, and we are assuming after long time system will be in equilibrium, and that expectation value, vacuum to vacuum transition expectation value, this is the path integral. That is our formula. So instead of x, now we have the variable phi, and this is the action. So let me write in a more appropriate way, d phi e to the power I h cut. Then I write d4x, and then half del mu phi minus m square by 2 phi square minus lambda factorial 4 phi to the power 4. This is our path integral in field theory. And this quantity we denote as, this vacuum to vacuum is called generating functional. We'll see why it is called generating functional, and z at 0. Because you also know that when we put some mathematical trick we use in path integral, that, okay, not 0 here. 0 I'll mention later. So okay, so z0 is like this, and z of j, that j I'll introduce e to the power I h cut s as it is, the whole thing, plus I by h cut jx phi x d4x. Okay, so if I introduce that, if you remember the j term I introduce in the, so then it will call j. When I put j equal to 0, I'll get j equal to 0. So this is the quantity we will now handle, and this will generate the propagator. It will generate 2-point function, 3-point function, 4-point function, etc., which will be useful for study our field theory. So first thing what we'll do, we'll start with this generating functional, and when we put, let me know, when we put z0 of j, then means equal to z of j. This is my notation, lambda equal to 0 for free theory. So we'll, at the beginning we'll deal with free theory, and then we'll put the interaction. So z, when I put a 0 here, that means lambda equal to 0, that means free theory. So let us start first with the z0 of j. So this will be d phi e to the power I h cut d4x. Okay, so half del mu phi minus m square by 2 phi square, okay, plus j phi, right? And z0 of 0, then this also will be 0. So now in the next class, I'll prove one important mathematical result, which will show you that Z0 is nothing but Z0 of 0 times e to the power minus I by 2h cut d4x d4 x prime j of x gf x minus x prime j of x prime, where this result I'll prove in next class. This is very important result, and I'll first do this a little bit. It will not take much. What is this GF? This GF is our old friend, that the Green's function or the propagator. The Feynman propagator. So this expression can be written in terms of this. So this result will prove in next class. It will take some time. I thought we'll be able to do, but we don't have time. So do you have any question? Then we'll find that how to do the calculations. But before that, maybe first we'll derive this in next class. Next class is on Thursday, and then we'll give you the motivation why we want to find Green's function or different Green's function, 2-point, 3-point, 4-point Green's function. That I'll motivate you through quantum electrodynamics that I left here. So quantum electrodynamics. So I'll give you a brief introduction of Feynman diagrams. and in quantum electrodynamics, and then we'll go to this. First we'll derive this, then we'll give the Feynman diagrams. This is important to motivate you. Later this Feynman diagrams, etc., will study in detail, systematic way when we start doing the quantum electrodynamics, another field theory. But first we'll do the simplest field theory, scalar field theory, and then we'll go to that. But Feynman diagrams and its usefulness, Feynman diagrams and also usefulness to calculate the quantities, calculate various in field theory. This is very important. See, idea is that, see, how you deal with this. When you have the interaction lambda 5-4 theory, this is called lambda 5-4 theory. So lambda 5-4 theory, lambda you have to assume small, and then you have to do perturbation. There is no, see, in field theory, any interaction, even in one body problem, any interaction is very difficult to solve. And one has to rely on perturbation technique. Electromagnetic is very successful, that electromagnetic theory, that quantum electrodynamics is the most successful quantum field theory, because that fine structure constant, that alpha in electromagnetic interaction is very small. You know, 1 by 137 is very small. So any field theory, you have to do perturbation, and the coupling has to be small for perturbation. For example, quantum chromodynamics, particle physics student will learn this. This is the theory of strong interaction. Theory of strong interaction is called quantum chromodynamics. It is behavior of the quarks and gluons, and they interact through strong interaction. Their coupling is strong. Its coupling is not small. They are strong coupling, and perturbative method fails here. So you need the non-perturbative methods. So that is why QCD will be difficult in that sense. Okay? QCD will be difficult in that sense. to study, because coupling is large. But coupling is small in the quantum electrodynamics, so that is why. And this lambda will assume here is small and will do the perturbation. What Feynman did, so perturbation theory, you know that anything will be written as lambda to the power 0 order, then there will be some quantity lambda to the power 1 order, lambda to the power 2 order, and this calculation, finding these terms, see, you already know that how difficult it's calculate the second order correction in the energy in the in perturbation theory in quantum mechanics, which is a finite degrees of freedom, 1 degree, 2 degrees of freedom. Now you have infinite degrees of freedom, so these calculating these quantities will be extremely difficult. So Feynman gave some diagrammatical approach to calculate this. That I'll first tell you to motivate you, and why we need to calculate, that I'll motivate you, then we'll do these calculations. So maybe I'll stop here unless you have some quick question. No, we at the moment argument is that we are considering the simplest possible. Momenta interaction will be further complicated. Yeah. Any other interaction which is invariant under Lorentz transformation and Gauss transformation, it is possible. This is the simplest possible, and later people, whether will take this interaction or that interaction, also will come, feedback will come from the experimental results. That experimentally you observe something after calculating in this interaction and whether it is matches or not. So suppose we consider lambda 5-4 theory and we calculate some physical quantity which can be measured experimentally. If they don't match, then we'll discard that lambda 5-4 theory interaction. We'll look for another interaction. But fortunately, this interaction gives good agreement with the experiments. Okay, so let me end the class.